Please tell me. Huh? Are there any doubts? Yes or no? At least you said yes, or at least you said no. What is? Hello?
Sir,
Yes.
sir, are the means the values we have taken for x dash t and y dash t as 1a, they depend on the particular equation that we have taken.
No, I cannot hear you. Tell me again. Huh?
Hello. Yes, sir. Sir,
Huh?
I'm saying that the equations like x dash t equal 1 and y dash t, we are giving some particular values to them. So they are particular about the PDE we are taking, right?
Particular values, it depends on the coefficient of the ux ui, like that, right? You remember?
Yes, sir. Yes. Yes,
Yeah,
sir.
it depends. Of course, it depends on the PDE. If the coefficients are different, then we have dx by dt, dy by dt are different. Okay.
Okay, sir.
So today I will give a more geometric way to tell you what is that. So just recall something. So just recall what we did. One of the examples. Recall. The example is this. Just recall this example. That ux xy plus uy xy is equal to 0 when xy is in R2, and you see that u of x naught 0 is gx when x equal. So your data is given, the initial data is given along this line, right? Along this line. This is x, this is y. So your initial data is given here, that x comma 0. So here, see? So the initial data x comma 0, it is given gx. Okay. Okay. So how we solve it? We take any curve. Consider any curve. Let gamma t is xt yt. Okay. Then what we did? We defined vt as a composition u of gamma t. That is nothing but u of xt yt and then v prime t. So what we did then? Then we did v prime t, that is x prime t at ux plus y prime t uy. Now let's assume that u satisfies this equation. So it is like that. Hello, can you hear me? All of you? Hello?
Yes, sir.
Yes.
Okay,
Yes, sir.
good, no problem. Okay. So now we assume that u satisfies this equation. If u satisfies this equation, if I assume x prime t is 1 and y prime t is 1, then v prime t is nothing but 0. Where it is 0? V prime t is 0 along the x prime t and y prime t equal to 1, along the curve whose derivatives are x prime t equal to 1 and y prime t. One component of its derivative x prime t and y is the second component. So when it's x prime t is 1 and y prime t equal to 1, along that curve, we don't know what is that curve. Along that curve, v prime t is 0. That means vt is constant. It means vt is constant. That is u of gamma t is equal to a constant along x prime t equal to 1 and y prime. So what we have to do next? We have to find what is x prime t and y prime 1. What is the equation? It is x prime t and y t prime, so that we can explicitly see what the curve is. And if we do that, t plus x naught, sorry, yt is t plus y naught. And what is this? Then gamma t is nothing but ordered pair xt yt. And what is gamma t? It's a straight line. The straight line whose slope is, what is the slope? Whose slope is? Come on, what is the slope?
1.
Whose slope is 1. Whose slope is equal to 1. Okay? Along these lines, that means along these lines, the solution has to be, necessarily the solution has to be a constant. That means if you draw the curve, these are the lines. Slope 1, let's say. This is 1. This is a straight line with slope 1. So along that curve, the value of u is constant. That means the value of here is equal to the value of here, and that is equal to the value of here. Now try to get a solution. Now try to get information from the data, given data. What is the given data? U of x naught equal to 0, sorry, g of x. Okay. If we do that, what we will get? Now you know how to do this. So now you have to, because we have find that u of xt yt equal to 1, some constant. Okay. Now we have to find u is constant along this slope line. Now we have to find u of xy, any point xy. This gives you only along this line. So now you have to find any point, any arbitrary point xy in your domain. So what you have to do? You take any point xy. You just drop a straight line whose slope is 1 and hit the x-axis. Hit the x-axis. And now try to take the information from here. Okay? You understand how this is very nice. So u of xy is nothing but, you know how to do this. That is u of xy is u of x minus y comma 0. You know y x minus y. So it is g of x minus y. U of xy equal to g of x minus y. This is the solution. Now we would like to do this in a, this is just a particular example. So there should be some theory behind this, right? So what is actually happening here? Okay, this is a very beautiful idea from geometry comes into play. Okay, let me do that.
Sir?
Now we will do, yes, yes.
Sir, can we go to the previous page?
Yes, sure, sure.
Yes. Sir, in the last line, how you have written this u x comma y is equals to u of x minus y comma 0?
Why? You tell me why. No, I will repeat. Why? Can just try. So what we know? No, this is nothing. It's a good question. So just think. You know the u is constant. The solution has to be constant along this line, right? Yes or no? Because
Yes.
u of xt and yt equal to constant. When xt and yt is gamma, that is a gamma t, u of gamma t. When it is a straight line with slope 1, it is constant. But this does not give you the solution, because you have to find u of xy any arbitrary point xy, right? Not along any curve. So you just take any point x comma y. Yes or no?
Yes.
Now what you have to do? You have to find the solution u of xy. So what you can do? You can draw a graph. You can draw a straight line which passes through xy and which hits this axis. Yes or no? This you can draw. This xy is any xy. Okay. So for any in this domain, you can always draw a graph, or always draw a straight line whose slope is 1 and hit this x-axis. Yes or no? You can do that.
Yes, sir.
Okay. So what is the equation of this straight line? Tell me.
Got it, sir. Got it.
Huh?
Got
What
it.
is the equation of, huh?
Got it, sir. I understand.
You understand?
Yes.
Sure?
Yes.
Okay. So this is actually a straight line x minus y equal to this one, right? Good. Okay. Now let me do it in a, this is just an example, as someone said that it depends on the PDE, right? Yes, it depends on the PDE. Now we will do more formally the theory behind this. Okay, you understand? Now what is happening? Okay, now we will do the theory behind this this methods. Okay, unless you want to do it, this is called methods of characteristics. Method of characteristics. Why this name? I will tell you. This is called method of characteristics. Okay, this is called method of characteristics. Okay, consider a general PD. Now we will do a theorem, not the example. Okay, consider the PDE in two variables. Okay, A x y u, general PD I am taking, B x y of u, u y is equal to C of x y of u. Which type of PD is this? Anyone?
Quasi linear.
Exactly, very good. Where A, B, C are continuous function, continuous functions in which variable? X, y and e. It means A of x, y, u of x. So there are three variables, three unknowns. Okay. Okay. Now, okay. So this is our motivation. We want to solve this PD. Of course, when I am talking about the solving some PD, you need to prescribe some what? What?
Domain.
Only given PD will not give. It should have some
Boundary condition.
Exactly. That means our aim is we wish to solve the above PDE with some boundary or some boundary condition. That is u of with a prescribed with a prescribed boundary condition. Okay. Sometimes it is called boundary condition or sometimes it is called initial condition. You can conditions. Okay. Okay. Good. Now this is our aim. So given a PD with we will come to that. What is that boundary condition? So let's say u of xy equal to some h of xy. Okay. So there is some boundary condition. We want to solve this type of PD. This is a quasi-linear PD. We want to solve this. Yes. Okay. Now let me digress from this PDE to some calculus. Recall some fact from calculus. Recall some facts from calculus. Several variables. Okay. Okay. Good. Suppose I say some set S. U is a C1 some function. U is a function C1 of, let's say, R2. You know what is the meaning of C1. Let us define a set of x, y, z such that z is equal to some function u of xy. For some function, for some C1 function u. Yes or no? This is what is this set called? Anyone? What is this set called?
Graph. Surface.
Surface, yes. Or more specific, yes, this is a surface. More specifically,
Graph of U.
exactly. Graph of, this is, and he is also said this is called surface or a graph. Okay. Graph of U. This is, you can show that this is a, of course, this is also called a surface. How it looks like? This looks like this, like this. Some, this is, let's say, this is Z, this is X, this is Y, right? So this is the, so here's, let's say, some domain omega. Okay, so this is a domain and Z of uxy is the graph of this sun. This is a graph, like just like in one variable. What is that? X fx. So if f, just remark if f is a map from R to R with, I say, some graph of, what is the graph of f? It is defined as the set x fx such that x belongs to R. So what we draw in actually when we draw the picture, so fx, when we call fx equal to x square, how it, x square by 2, how it looks like this. What is called? This actually is, this is the graph. When we are drawing something on the paper, That is a graph of some function. But here we cannot draw in the paper because why? Why? Why?
Paper is two-dimensional.
Exactly. This is a two dimension. That's why we can draw this graph x f x. But here we can just visualize this. So this is a x and this u is a function of xy. So when we are talking about z equal to uxy, then this is a uxyz such that z equal to uxy. This is a graph in 3 dimension in space. This is a space variable. Okay, very good, very good. Now you tell me what is the normal to let us take a let us consider a point. Consider a point in that previous surface point. Let us consider a point x naught, y naught, z naught belongs to S. That means that is z naught is nothing but u of x naught, y naught. Okay. Now you tell me what is the normal at the point x naught, y naught, z naught. Who knows? What is the normal at the point x naught, y naught, z naught of the surface? This is a, as you say, this is a surface. So let's say this is point x naught, y naught, z naught. So what is the normal n? Tell me, what is the normal? Huh?
Perpendicular to the surface at that point.
Perpendicular to the
Surface at that point.
Tangent plane.
exactly.
Tangent plane at that point.
Very good, very good. This is the tangent plane. Okay, very good. So what explicitly in the when it's a graph, then you can explicitly see what is the normal. Can anyone know?
So partial derivatives like
Just what is
ux
the meaning of
comma
partial? Yes, yes, you tell me. Yes, yes, very close.
Gradient.
You say one said gradient. Someone says, another says. Yes. So someone is saying a partial is right. Tell me. You are Atharva. You tell me. You are close.
so I think it is ux comma uy comma minus 1
Ux at the point x naught,
x
y naught, z naught. U oh sorry. U of x naught, uy minus 1. Okay. Both are correct. And what is the gradient? Gradient means gradient of u, right? That is ux, uy. So something is then and 0 you are saying, right? Something you are saying, right? Actually, not both are correct. This is correct actually, but you can say that from the gradient only it comes from here. You can prove from here. When this is a very good question. When I am talking, let's take a different surface, S tilde. What is that? Let us say x, y, z, such that f of x, y, z equal to 0 for some f. C1 function. For this type of function, surface, this is also another surface. This is called level surface. Level surface, they are called. For these level surface, gradient is gradient of f at the point x naught, y naught, and z naught is a normal. You are right. You should have done this in the course in calculus, in several variable calculus or real analysis. It's a real analysis course. But this is a graph. This S, what we are considering S, is nothing but it's a graph. It's not a level surface, right? But you could make, so you know what is the proof why for a level surface this is a normal, gradient of f is a normal. Who knows this proof? Huh? Who knows this proof? Should I do this proof? Or you know this proof? Please tell me. Come on. Otherwise, I don't know. You want me to do or You know this proof. Tell me. For a level surface.
Here f equals to u minus z.
Exactly. Exactly. For this proof you know, right? Everyone knows this, right? Or I should repeat? Tell me. Yes or no? Please tell me. Please, I request you to please tell me. You want me to prove this? This for the level surface y gradient of f is a normal?
So we can try.
Okay, you try. So you should tell me that you should want to try. Okay, try. So once this is known, you know. Can you now do this for S? As someone said that you can. What is S? In our case, S is x, y, z, such that z equal to u of x, y. You can write this as a level surface. How? You can write this as x, y, z such that f of x, y, z equal to 0, where f of x, y, z is nothing but u of x, y minus z. Clear? So now you convert this surface to a level surface. So you make this graph as a level surface for some f, which looks like this. Now you know that for the level surface, the normal is gradient of f at the normal at the point x naught y naught is this. That means this is del f by del x, del f by del y, del f by del z. Now you know that you know now for explicitly f you know that it is u of xy minus z. So what is del f by del x? Anyone?
Ux.
Del u by del x, del u by del y, and what is del f by del z?
Minus 1.
Now this is nothing but ua. Of course, these are all derivative at the point x naught, y naught, z naught. Uy minus 1. This is the normal at the point x naught, y naught, z naught. Clear? Is it clear to all? Anyway, it is clear, I guess. Okay, so this is the normal. So if I say that S is given by x, y, z such that z is equal to u of x, y, the normal, then the normal to the surface S at any point in any arbitrary point x naught, y naught, z naught is nothing but n naught. N naught is given by ux at x naught, y naught, uy at x naught, y naught, comma minus of 1. Clear? Clear. So you just draw the graph. This is x naught, y naught, z naught. So normal. Now what is the equation we try to solve? Is a of x, y, u at ax plus b of x, y, u of bx, ux and equal to c. You want to solve this equation. This is in your mind, right? So normal is ux, uy minus 1. Now you tell me, consider the vector, consider any vector, consider the vector v naught as a of x naught, y naught, and u of x naught means z naught, b of x vector on the surface S. Consider a vector on the surface S. and C of x naught, y naught, z naught. We consider a vector. Okay. Observe that the vector v naught is a of x naught, y naught, z naught. Of course, this lie because z naught is now by u of x naught, y naught. Okay. Consider this vector. Okay. This should I say that is perpendicular perpendicular to the normal n naught if u is a solution to the PDE. Agree or not? You agree? All of you agree or not? All of you agree or not?
Yes, sir.
Why? Because what is the normal at n naught? It is nothing but ux at x naught, y naught, uy at x naught, y naught minus 1 should width of a, b, c should be equal to 0, right? Yes or no? If is perpendicular to this, of course, if u is because this gives you aux plus buy minus c equal to 0. That is aux plus buy equal to c. Agreed? All of you agreed? All of you agreed? Yes or no?
Yes.
Are you following or not? All of you, please tell me. Unless you tell me, I cannot understand. Anshu, Ajay, are you following?
Yes, sir.
Ritika, are you
Yes.
following?
Yes, sir.
Yeah, this
Yes,
is
sir.
nothing. Okay, good. So ux at dot a dot this is 0. That means just a minute, means this imply that if u is a solution, then this dot product is 0. This imply v naught must lie on the tangent plane to the surface S at x naught, y naught, z naught. Because we know that normal is normal dot ux uy minus 1 dot a b c equal to 0. If u is a solution, always you assume if u is a solution to that PDE, then this dot product is 0. And we know that this is a normal. So it has to, this lie should lie between, this should lie lies to the, this should lie in the tangent plane. If u is a solution, tangent plane. If u is a solution to that PDE, then this dot product is 0, and we know that for that surface ux uy and minus 1 is a normal. That means this vector should lie on the tangent plane. Okay. Now your problem of solving this PDE will convert to a problem in finding some surface. How? M. Find the surface. So to solve the PDE is equivalent to find the surface. Find the surface Z equal to u of xy, that is the surface S. Knowing that the vector field V of x, y, z, which is your vector field A, B, C. Of course, at the point x, y, and z. Okay. What is the problem? Now find the surface Z. That is Z of u, x, y means S. Now find the surface S, knowing, because A, B, C are given. That u1, 2, 3, that that A, B, C coefficients are given. That means to solve that PDE is equivalent to find the surface, knowing that the vector field ABC lies on the tangent plane of the surface S at the point XYZ. Such surface is called the famous integral surface. Thus, to find a solution to the PDE, to find a solution to that, you say it is equation or something, now name it equation 1. Okay, name it. To thus to find a solution to equation 1, we should try to find the integral surface. Integral surface. Is it clear or not? Please tell me, is it clear, all of you? You can ask me 1,000 times, I will answer. I will answer. Tell me. This is very important. You understand or not? Or I should repeat again? At least you have to speak up. I should repeat again, or all of you understand?
Can you summarize, sir, once again what we have done and what we have intend to do?
Okay, good. We want to solve this PD. Want to solve. Okay, agreed?
Yes,
We want to solve this PD. It is equivalent to find a surface S it is equivalent to find the surface S knowing just a minute. Equivalent to find the surface S knowing that the vector field lies on the tangent plane of the surface. Agreed or not? We want to solve this PDE. Ax, y, u, ux. Man, that what is the unknown? U is the unknown, right? Right? U is the unknown. That is equivalent to find the surface S. Of course, surface S means we have to find U, knowing that the vector field ABC lies on the tangent plane of the surface. You are agreed or not? Agreed or not?
Yes.
Yes. Clear? Because this vector field ABC, this is given, right? ABC. Of course, U is unknown, but lies on the tangent plane of the surface. So what is the normal to the surface? This. That means ux, uy minus 1. And we assume that ABC is a tangent at the tangent plane. So this ABC should be 0. That is equivalent to this PD. Agreed? Just write down ux dot a, uy dot e. Clear? That means to solve a PD is equivalent to find a surface. Now you are converting this problem of PD to a completely a geometric problem. Okay? Okay. Okay. And such surfaces are known as integral surface. Now let us write down a more specific problem. Not specific, the same problem with a boundary condition. This is called Cauchy problem. What happened? Just a minute. Cauchy problem. What is that? Given a space curve, gamma in R3. So gamma will be of 3 component, okay? Xt, yt, zt or something like that. Whose projection? What happened to the pen? Whose projection on the plane is gamma, small gamma? You understand this meaning? Given a space curve gamma in R3, whose projection on the plane is gamma. Who will tell me what is that meaning? Huh? What is the meaning of that? That means sum of the either x, y, z. So gamma is R3, the 3 component. So projection means at least one of the component is 0. You understand? Projection is gamma. Find the function. Find a function u satisfying 1. That means 1 means you know what is that, ax plus by plus aux plus b uy equal to c, satisfying 1. Problem with the pen, just a minute. Such that the surface z equal to u of xy contains gamma. In other words, find u of xy means find u of xy satisfying this. AUX, A is not a constant, you know what is the A. P of Ui equal to C in some open set U such that, and what is the boundary? U of xy is given some U of, is given some H of What happened, man? Switch off. U of xy equal to find ux and satisfying the equation, and the boundary condition is, or the initial h of xy on gamma. Sorry, I'm very sorry. Writing is very bad. Please let me know. Did you understand? Please let me know.
No, sir. Can you repeat this one?
Because my pen is stuck. I don't know why. Because of the internet or something, my pen is stuck completely. Okay. So you have to find u of. Very sorry. Pen is not working. Cauchy problem. What is the Cauchy problem? Given a space curve gamma. Okay, clear? This line is clear? You have given us some space curve gamma whose projection on the plane is small gamma. Either it can be in xy plane or yz plane or xz plane. You understand? Space curve means there is a three component. Now we are projecting that curve to some x plane or y plane or xy plane or yz plane or zx plane. Is it clear?
Yes, sir.
Okay. So this is given. Now find a function u of xy satisfying 1. 1 means our equation. That equation. Axy ux plus by uy and cxy this. This is your y. Satisfying y such that the surface contains gamma. Gamma means, what is the meaning of this? Given a space curve? The surface contains gamma means what does it mean? What does it mean? A surface contains gamma. What does it mean? Can anyone tell me? What does it mean? The surface contains gamma. That means, what is that? That means the space curve gamma should look like x something x y z, where z the third variable should be given by u of some nu t. You understand? You understand?
Yes. So,
The surface contains gamma. That means gamma should lie on the surface. Yes. What is gamma? Gamma is a space curve. Gamma should lie on the surface. What does it mean? X, Y. So what is the any point on the surface is X, Y, Z. So gamma lies on the surface means the for gamma there are three components, right? Xt, Yt, Zt. So Zt we should write Zt in terms of u of xt, Yt. You understand?
Yes, sir.
So in other words, what does that mean? In other words, analytically, it means that you find u of xy satisfying this PDE and u of xy equal to h of xy on the gamma is small gamma, because u of xy equal to small h gamma. What does it mean? Because xy is now in two variable, so on gamma. So it is a projection on. So this gamma is a projection of gamma onto xy plane. Clear? Projection of capital gamma onto xy plane. Is it clear? That
Yes.
means we want to solve this PDE. A of ux plus b uy equal to c and u of xy. It's a boundary condition. U of xy is given to be h of xy. Clear? Is it clear?
yes, sir.
Yeah, good. Clear? Okay. Anyway. So now we want to solve this in terms of in this geometrical way. Sorry, I have a problem with my pen. So this is always becoming hang. Okay, anyway. Okay, so let us draw the picture. Okay. You want to find this surface. What is small gamma? Gamma lying in xy plane. This is x, this is y, this is z. You want to find z of u of xy. Okay? Given that u of xy is equal to h of xy in this plane. In this plane. Okay? You want to find surface x, y, u of xy. Okay? We want to find this surface satisfying that PDE. This is the geometrical meaning, and it is given. This is given. This is given. U of xy equal to h of xy is given on this curve. On this curve. On this curve. Okay? That gamma. What is that gamma? And where is the capital gamma? Capital gamma lies here somewhere here. This is your capital gamma. And this is a projection of this gamma. This is a projection of this gamma. You understand? There is some gamma. It is given. You want to find a surface S. This is given. Capital gamma is given. This is your capital gamma. And what is small gamma? This is your small gamma. With projection of capital gamma on the xy plane, you have to find a surface xy u of xy such that capital gamma lies on this surface. Is it now clear, all of you? Yes, clear? Yes or no?
Yes, sir.
Yes.
Okay. ठीक है. Now let us prove this. Now let us do it formally. Okay. Okay. What happened to my pen today? It's not working, man. Let us assume that the surface S is parametrizable. Okay. Parametrizable, and S is parametric like this. X of st, y of st, and z of st. Z of st. Let us assume we have to find this S, okay, with t positive. Just a minute, it's not at all working. Okay. With t positive and S belongs to some interval I. Okay, that means we have to find the surface S with x of s. This is I parameter x, y, z. I just parameterize this at x as x of xt, y of st, z of st. Of course, z of st is given by x of u of x of st, y of st. You know what is the meaning of that. Okay. Okay. Now I think it will work. Let the initial space curve. Because your space curve is given gamma. X of S0, Y of S0, because st, I take the initial at t equal to 0, okay? and z of, again it started. Z of this. Okay. Again I am writing x of S0, y of S0, z of S0. Okay. So this is the initial space curve, okay? Because this is your gamma. This is your gamma. So there is a gamma, okay? Okay. This is your gamma, okay? So what is the gamma? What is small gamma? Can you tell me what is small gamma? What is small gamma? What is small gamma? What is the projection of gamma on the xy plane?
X of S0, comma Y of S0.
Yes, yes, very good, very good. So it is nothing but like this. X of S0, Y of S0, 0. Okay, this is x in a xy plane. Anyway, okay. Now given okay, given initial condition u of xy h on gamma, okay, that is, this imply, what is this imply? What is u of xy? Equal to h of h on gamma. What does it mean? Can anyone tell me? U of u of x S0, y of S0 is equal to h of xy. That means x of S0, y of S0. Clear? Yes or no? It is given, right? U of xy equal to h of xy on gamma. What is gamma? Now is your, this is your gamma. Yes or no?
Yes.
This implies z of S0, u of x0 is S0 is z of S0, because the surface we want to find, right? That is some hs of s. This is, I name it as h of s. Okay, this is a, I define to be h of s. Okay. Now we denote. Let us we denote. Sorry, today my pen is not working. I don't know why. Maybe because of the internet here is slow. I don't know why. We may assume. We may assume x of, I just name it. Nothing. This is just f of s0. F of s. This is just a notation. Okay, f of s, and y of s0 is nothing but g of s. These are notations. Okay, because x s0, y s0. Now, since we know that ABC is perpendicular to the normal, to the surface S. This implies ABC this implies ABC is proportional, this vector ABC is proportional to the tangent vector. To the tangent vector. Agreed or not? To any tangent vector. Tangent vector. You agreed or not? Because why? Why ABC is proportional to a tangent vector? Huh? Why ABC is proportional to a tangent vector?
Insofar as ABC is normal.
Exactly. Exactly. Because ABC is normal to the. So what is the tangent vector? Can anyone tell me? What is the tangent vector of the surface? Because I have denoted the surface like this now. X of ST, Y of ST, Z of ST. What is the tangent vector to this S? Huh? What is the tangent? What is the tangent vector to the surface S? Which surface is given by this? Huh? dx by dt, dy by dt, dz by dt. Agreed or not? This is a tangent vector. This is a tangent vector. Tangent vector. Tangent vector. Okay. So now this tangent vector is proportional to ABC. What does it mean? Huh? That is dx by dt is A of x of st at the point y of st, z of st. dy by dt is b of x of st, y of st, z of st. Oh, sorry, this. And dz of dt is c of x of st, y of st at the point yst, and z of at the point st. Okay, subject to the initial condition. Subject to the initial condition, x of S0 is Fs, y at S0 is Gs, and sorry, very sorry today, because my pen is not working at all. Okay? So you have a system of ordinary differential equation now. dx by dt is A, dy dt equal to B, dz by dt equal to C, and x S0 is Fs, y at the initial condition at, because whenever we are studying ODE, we need to assign a initial condition. X S0 is Fs, just denote it. Y S0 is Gs, and Z of S0 is Hs. Is it clear? Now,
Sir,
this
why the coefficient is 1? Means they are proportional, so we
So
can take
lambda
any.
times, so dx by dt should be lambda times lambda 1 times lambda 2 times lambda 3. But we have an initial condition, right? So you can directly input this initial condition and make it lambda 1, lambda 2, and lambda 3. Clear? Clear?
Okay.
So you have you lambda 1, lambda 2, lambda 3 is there. But as you know that we know the initial condition, let's say Fs, Gs, and Hs. So once we have ABC, you solve with lambda 1, lambda 2, lambda 3. Now once you put x, you will solve this ODE, and you put it, if you want, you can put some lambda 1, lambda 2, lambda 3. Clear? Clear? Now since we have a initial condition, you can solve this lambda 1, lambda 2. So I don't want to complicate it. So it is like a this. Clear? Okay. Is it clear, Yash?
Yes, sir.
Okay. Because all the initial conditions are there, we can impose all these conditions and can solve that lambda 1, lambda 2. Okay. Anyway, so now the problem is, this is the problem here. Whenever some PDE is given, you can write dx, dy, dt, and we can solve this ODE. So now the question is, whether this ODE has a solution or not. You tell me why whether this ODE has a solution or not. Tell me. Please let me know why. Under which assumption this ODE will have a solution? Huh? So nothing but, so this is ODE, you can see. That is why I say Picard's theorem. We can solve this system of equations uniquely via Picard's theorem for all small t, not all. Picard's theorem gives you the existence and uniqueness will be given in a small neighborhood of t, right? In a small t under the assumption ABC are Lipschitz, okay? In term, or you may write down ABC, the coefficients are C1 function. Okay, you know this, right? When there is a Lipschitz condition is there, then you can solve this PODE in a small local existence and uniqueness. You know all of you? All of you know?
Yes, sir.
Others, Ashish, Ekans, Anshu, Ankit, do you know? Shomitra, all of you know?
Yes, sir.
Okay, good. So to obtain the now, so what you have obtained now? Now what we have obtained? You have find x of st, y of st, z of st. Right? You have find this. Where? And you know that z of st is nothing but u of st. Well, you know what is that? What is that? Okay. Now you have find for small time because this t is small. For small time. So for small time you have found out this. But now we have to find what we have to find. We want to. So what is like this? Like this. So you have a given curve capital gamma. Around this curve capital gamma, this you find this some other curves, right? This is this capital gamma is the initial curve, and you find some curve, right? And this union of this curve will give you the surface. So this is the union of curves. Just think union of curves. Union of curves gives you the integral surface. Gives you integral surface. You understand why? How we get? So you get gamma. This is your initial curve. Okay. So this is your initial curve. Now near t, here t is 0 for the initial curve. T is 0. So what the ODE gives you? Near t you have a solution. That means near t you have a curve x of st, y of st, z of st. Clear? Is it clear? So that means you have some curve near t. So you have a surface. So when gamma is given at near t equal to 0, you have a surface. Now you take all the union of those curves, and you can see that those, if you take the union of those curves, you will get a surface, and this surface is known as the integral surface, which we would like to obtain. That is the solution of that PDE. The integral surface is the solution of that PDE. You understand? Okay. Now, but your life is not over. Your job is not over. You have only found out for some ST because you have parameterized the curve. Now you have to find in terms of x and y mathematically. What I say that you take the union and you make a surface, but this is not mathematics. It is just a pictorial way that you find one curve. If you take all the union of those curves, it will form a surface, right? But now you have to do it mathematically. That means now you have to find the integral surface. That means what? To obtain the surface, obtain the surface in the variable xy now. In the variable xy, we need to invert the map. We need to invert the map. To obtain the surface in the variable xy, we need to invert the map ts. That means, so xy is given. What you find? You find x of ts, y of ts, z of ts. But we want to find, or whatever. Yes, we want to find u is, want to find this, just like our example. Again, the problem. Okay. Now we want to find u of xy, not xt or y2. So you want to invert. We want to invert the map xy to ts. Now we want to find in xy. So now we want to invert, same thing what we did in the example. We want to invert the ts variable to xy. How to do this? Anyone? When this ts xy, you have to tell me this xy. You have to find in terms of ts. Sorry, st. Same thing. St. Now we want to invert it. When it can possible? When we can invert this? When we can invert this map? Invert this map. Huh? When we can invert this map?
When the map is budgeted.
When? Yes, when?
The derivative of f is non-zero.
Something. We have to recall the inverse function theorem. For this, that is why last class I said that please have a look on the inverse function theorem. For this, we use inverse function theorem. The above, that means this is in terms of xts, yts, right? X of ts, y of ts. Okay? The above map is invertible near time t equal to 0. Near, because we want to find near t equal to 0. Near t equal to 0 if the Jacobian is not 0 at time t equal to c. What is the map? Your map of, what is your map? xy is given by x of ts or st, y of st. Right? When this map is invertible at time t equal to 0, when the Jacobian is non-zero. Now, what is the meaning of it? Jacobian of this map? What is that? What is the Jacobian of this map? Anyone? Del x, this is x. Del x by del s, del x by del t, del y by del s, del y by del t. This is the model. This is the matrix, and take the determinant. This is called the Jacobian. If this Jacobian is non-zero, that is del f by this map, x of st, y of st. If this map is, if this Jacobian is non-zero, we can invert x of st, y of st to x of y. You understand? So there is a map. There is this x st, y of st. Now we have, because we have solved here, you have to convert it here. That means you have to convert. So there is a map f inverse from x of st, y of st to xy, if the Jacobian is non-zero. Okay, that means what is the Final conclusion. Final conclusion is to solve this PDE, we have to solve this problem. Dx dt equal to A, you know, dy dt equal to B, dz by dt equal to C. Gamma is the given curve. Let's say gamma gamma is your the given curve. Okay, gamma is the given curve, given space curve, which is the initial curve is of course x of is 0, y of is 0, comma z of is 0. Okay, and what is x of is 0? Under the assumption x of is 0 is f of s, y of is 0 is g of s, and z of is 0 is, this is h of s. So this is your PD, system of PD with the initial condition. This system will have a, first of all, Picard's theorem, first step. Step 1, you have to solve this one. You have to solve this PD. Okay, Picard's theorem. Picard's theorem gives you a solution. Picard's theorem, existence plus uniqueness. Okay, existence plus uniqueness. Uniqueness, for uniqueness you need A, B, C. The coefficient should A, B, C should have a C1. Okay, uniqueness. Okay, step 2, you have to find the Jacobian of x, y, z, xs, xt, yt, st. Okay, once the Jacobian is non-zero, we can invert it. Then you have to check Jacobian. Jacobian not equal to 0, we can invert it. You have a solution z equal to u of xy. Now is it clear or not? You tell me. Now, if you don't want to do it in a geometric way, at least this is the final conclusion we have. Dx of dt equal to A, dy by dt equal to B, dz to, these are not constant. This is of course x of st, y of st. This. You have this is a system of ODE. If a given curve gamma is x0, y0, 0, Picard's theorem gives you existence and uniqueness of this ODE, provided the A, B, C are a C1 function. And step 2, we have to check the Jacobian of this map, x of st and y of st. Once the Jacobian is non-zero, we can invert it and you can get z of u of xy. Now you tell me, is it clear or not? All of you.
Locally invertible. Locally invertible or invertible in the
locally, because existence and uniqueness of Picard's theorem. If you remember and go to the ODE notes, you will see that the Picard's theorem is for s equal to 0. That means near t equal to 0, you can get a solution. Okay, near t equal, this is not a global solution. You remember from 0 to t max. You remember this is your t max, maximum interval. You remember? Near t equal to 0, Picard's theorem gives you existence and uniqueness. And Jacobian you have to check near t equal to 0. That means at t equal to 0. You have to check the Jacobian is non-zero at t equal to 0. If t equal to 0, the Jacobian is non-zero, then the inverse function theorem says that around t equal to 0, you have an inversion. Clear? Everything is local.
The curves give us the surface, but how we guarantee that we can't go infinitely many times? Take the t.
That is a different story. That is because this depends on the problem. This depends on the PDE. Okay, you can go infinitely. Means that t can be 0 to infinity also. Okay, that depends on the problem to problem. But for any general problem, this is at most you can do that. Okay, you understand?
Means for the infinite union, we can only imagine this thing, right? We can't.
No. If suppose you can invert it for all t, let's say, okay, then you can do that. And if you have a solution linear, if all the PDEs are linear PDE or ODE, sorry, if all are ABC linearly depends, it means that like dx by dt equal to 1, let's say, that means t equal to t naught plus s, right? For this exists for this ODE, the solution of this ODE exists for all t, right?
Yes.
For those, you can have a solution for all solutions. That means u of xy is in all of the domain. Okay, but if you want to solve it locally, at least this theory says, but theoretically you can say that locally you will have a solution. Locally you have an integral surface once the space curve is given. You understand? Once the space curve is given, you have a local. This local existence is guaranteed. But if the PD is linear or a semi-linear, you will see that that can be done. But if it's a quasi-linear, you will see that that cannot. We will do many examples. Once the PD is quasi-linear, you will see that this integral surface does not exist for all xy. Okay? You understand? There will be a infinitely many things will come. Okay? You understand? All of you understand? All of you understand? Hello?
So general equation we are getting for surface.
Yes, yes, tell me.
Means we are finding surface locally. Right?
Yes, 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 yes. At most you can do that, but in some cases you can have a global also. Okay. 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 Now more definite. So this is the thing. We will do many examples.
Hello,
So
sir.
that yes, yes, yes. Please.
Sir, you took the parameterization of data curve at x of s0, y, x dash of. So the second variable was 0.
Why?
But that is possible only when the initial condition that was given, that is the data should be given at u of x0, no?
No,
But
that
you
is why
took u of
I have
xy.
not. Right. Good question. See. So your gamma is this is the initial curve. What is the gamma? X of t s0, y of s0, z of s0. All three variables are there. Okay, you just draw this curve. This is your initial curve gamma. Okay. Yes. These are three components are there. I am not claiming that it is in xy plane or yz plane. Okay. This is a parameterization. You have to understand. This is a parameterization of the curve in R3. How the curve in R3 looks like. You have xt, yt, zt, any curve, right? This is any curve in R3. But I have to parameterize in a different way. I am putting s0, y0, and s0. Clear? Okay.
Sir, but for
now,
that the boundary condition should be given at u or u of x0, no?
No, it is given u of boundary condition is it is given u of xy equal to h of xy. Yes or no? What does it mean? U of x of s0, y at s of 0. Xy is nothing but x of s0, y of this is a parameterization of x, y. This is h of z. Clear? I name it as h of s. Clear? So what is x? What is x of s0, y at s0? This is your curve gamma. This is the projection. This is the projection of capital gamma onto xy plane. Clear? Is it clear? So this is gamma. This is a plane R3 space curve. You project it in the xy plane. Okay? If you project it gamma to the xy plane, what will be it look like? It is 0 in the z variable. This is your gamma. Along that gamma, the initial condition is given. That is, u of gamma is given h of gamma. That means u of this x of s0, y of s0 is given that this is h of same thing. That is, I name it h of s. And what is u of x0, y0? Because gamma lies in the surface. That means z of s comma 0 is given as h of s. You understand?
Yes, sir.
Clear?
Yes, sir.
Is it clear? Okay,
yes,
very good, very good. Okay, okay, just one more definition, then I will stop. Okay. one more definition. So the definition is, oh, okay. So just the last, I write down the Jacobian, right? Del x by del s, del x by del t, del y by del s, del y by del t at time t equal to 0, right? What is del x by ds? Because we know that, right? X at 0 is fs. We know this, right? Y at s0 is gs, right? So what is this? And what is del x by del t? You know ABC. This is nothing but f prime of s, g prime of s, a. The determinant is b into f prime of s minus a into g prime of s, not equal to 0. This is not equal to 0 is equivalent to this is not. Clear? Is it clear? So now I tell a definition. This is very important definition. This is called non-characteristic curve. A curve gamma is called non-characteristic if b into f prime of s minus a into g prime of s is thus the curve we call characteristic curve if b of f not equal to 0. Okay. So a curve gamma is the space. Any you understand what is that gamma? This is the projection of capital gamma. Is a non-characteristic. You can check easily. You will see in that problem to problem. If this is so, a theorem says that this is a theorem. Let gamma be a non-characteristic curve. Whatever we have done in the previous slide, I write it as a theorem. Let gamma be a non-characteristic. That means that Jacobian is non-zero. Okay, and let a, b, c are C1 functions. Three variables. Okay. Then the Cauchy problem. Then the Cauchy problem is when the problem is given the initial or boundary condition. The Cauchy problem a of x y u ux plus b of x y u uy is equal to c of x y u in omega u of xy is equal to h of xy on gamma. This gamma is a non-characteristic curve. You understand? You know what is the meaning of a non-characteristic? That means the Jacobian matrix is non-zero for that curve. This has a solution. Now, as I write down, has a solution in a neighborhood of you understand? In a neighborhood of gamma. That means gamma is nothing but x of s0, y of s0 in a neighborhood of gamma. That means you have a solution x of st, y of st, and if you lift the curve in the z of st for t small. So all this theory says that it has a solution in the neighborhood of the non-characteristic curve. What is the non-characteristic curve? On the curve where the initial conditions are given on that curve. When we do like u of x comma 0 equal to h of x, that what is the characteristic curve? You tell me. What for this problem? Just we have solved, right? U of x0 is equal to hx. What is gamma? Who will tell? What is gamma? What is gamma? Huh? Gamma is s comma 0. And what is capital gamma? S comma 0 comma h of s. Understand? You understand? Yes or no? This is for this problem, for such problem. Now we will see how to solve. Where is this guy? So says that if this gamma is non-characteristic, If A, this is B, this is C. C is 0. In your case, C is 0, A is 1, B equal to 1. Right? C is 0, A equal to 1, B equal to 1. So all are C1 function. You have a solution near this gamma. That means gamma, you have a solution for ST for T small. But we will see that the theorem says only that. But case to case we will see that maybe this T can be extended to infinity. Maybe. It depends on the problem. It depends on the problem. So, but the theorem says that it will only have a small solution. It does not say that it will not have a larger solution. Okay, it's a necessary condition that you will have a teaser for T small, for near gamma you will have a solution. Well, now we will do many examples. Yeah. So this is now. So now tell me, did you understand or not? You try to go and check again, read this part and let me know. Okay. If you have any doubt, I will again explain. But this is just, I hope, sorry for the inconvenience today. My pen was not working good. So, but sorry, very sorry. But at least you understand. Please tell me honestly. Because I'm trying. Huh? Yes or no? Hello? Can you hear me? Hello? Can you hear me?
Yes, sir.
So, have you understand these things? Okay, you go home and check if you wish. Then anyway, now you have to tell me the date for the today is the final. So you have to tell me the date for the tutorial. Tell me when. Hello. Please tell me when we can conduct a tutorial. Fix the date. I'm repeatedly saying for every week. Please tell me, come on. Okay, then you don't have, then I will say that you don't need to have a tutor. I will ask the head to say that you are not willing to have a tutor, willing to conduct a tutor, you are not willing to have a tutorial class, right?
Sir, actually, some or the other time, some of other of us, we have classes at some or the other time.
But this
So
is, I
it's
am
better
saying
that
repeatedly
you.
for a week. I am saying repeatedly for a week so that you should fix a date. I say that 6:30, 7:30, anything is possible. You are not discussing among yourself. So if you wish, you don't need a tutorial, you tell me, I will not conduct a tutorial. Okay? Okay. I will tell them that you don't have to have it, you don't need any tutorial. Okay.
So you
Thank
can fix it in the evening at some time.
I'm repeatedly asking you people to fix it for a week.
Sir, there is no consensus in the class. Sometimes somebody is busy.
I said you fix it in the evening, anytime. I give you that flexibility. Okay, I fix it on Friday, 6:30. Whoever will come, or if you don't want to come, don't come. Anyway, thank you. I will write an email.